In numerical analysis, a branch of mathematics, there are several square root algorithms or methods of computing the principal square root of a non-negative real number. For the square roots of a negative or complex number, see below. Finding is the same as solving the equation. Therefore, any general numerical root finding algorithm can be used. Newton's method, for example, reduces in this case to the so-called Babylonian method. Generally, these methods yield approximate results. To get a higher precision for the root, a higher precision for the square is required and a larger number of steps must be calculated. Rough estimation. Many square root algorithms require an initial seed value. If the initial seed value is far away from the actual square root, the algorithm will be slowed down. It is therefore useful to have a rough estimate, which may be very inaccurate but easy to calculate, with expressed in scientific notation as where an n is an integer. The square root can be estimated as the factors 2 and 6 are used because they approximate the geometric means of the lowest and highest possible values with a given number of digits. And 4. The estimate is, when working in the binary numeral system, by expressing as where, the square root can be estimated as, since the geometric mean of the lowest and highest possible values is. For the binary approximation gives. These approximations are useful to find better seeds for iterative algorithms, which results in faster convergence. Babylonian method. Perhaps the first algorithm used for approximating square root s is known as the Babylonian method, named after the Babylonians, or heroes method, named after the 1st century Greek mathematician Hero of Alexandria who gave the first explicit description of the method. It can be derived from Newton's method. The basic idea is that if x is an overestimate to the square root of a non-negative real number s, then x will be an underestimate, and so the average of these two numbers may reasonably be expected to provide a better approximation. More precisely, if x is our initial guess of square root s and e is the error in our estimate such that s equals 2, then we can expand the binomial and solve for since. Therefore, we can compensate for the error and update our old estimate as since the computed error was not exact. This becomes our next best guess. The process of updating is iterated until desired accuracy is obtained. It proceeds as follows. Begin with an arbitrary positive starting value x0. Let xn plus 1 be the average of xn and xn. Repeat step 2 until the desired accuracy is achieved. It can also be represented as. This algorithm works equally well in the p-adic numbers, but cannot be used to identify real square roots with p-adic square roots. One can, for example, construct a sequence of rational numbers by this method that converges to +3 in the rails, but to -3 in the two adics. Example: to calculate square root s, where s equals 125,348, to 6 significant figures, use the rough estimation method above to get therefore square root 125,348 354.045. Convergence. Let the relative error in xn be defined by and thus then it can be shown that and thus that and consequently that convergence is assured, provided that x0 and s are both positive. Worst case for convergence: if using the rough estimate above with the Babylonian method, then the least accurate cases in ascending order are as follows. Thus in any case, rounding errors will slow the convergence. It is recommended to keep at least one extra digit beyond the desired accuracy of the xn being calculated to minimize round-off error. Digit-by-digit calculation. This is a method to find each digit of the square root in a sequence. It is slower than the Babylonian method, but it has several advantages. It can be easier for manual calculations. Every digit of the root found is known to be correct, i.e., it does not have to be changed later. If the square root has an expansion that terminates, the algorithm terminates after the last digit is found. Thus, it can be used to check whether a given integer is a square number. The algorithm works for any base, and naturally, the way it proceeds depends on the base chosen. Napier's bones include an aid for the execution of this algorithm. The shifting nth root algorithm is a generalization of this method. Basic principles: suppose we're able to find the square root of n by expressing it as a sum of n positive numbers such that by repeatedly applying the basic identity the right-hand side term can be expanded, as this expression allows us to find the square root by sequentially guessing the values of s. Suppose that the numbers have already been guessed. Then the mth term of the right-hand side of above summation is given by where is the approximate square root found so far. Now each new guess should satisfy the recursion such that for all with initialization when the exact square root has been found, if not, then the sum of s gives a suitable approximation of the square root, with being the approximation error. For example, in the decimal number system we have where are placeholders and the coefficients. As in any theatrical stage of the square root calculation, the approximate root found so far, and the summation term are given by here. Since the place value of is an even power of 10, we only need to work with the pair of most significant digits of the remaining term at any theatrical stage. The section below codifies this procedure. It is obvious that a similar method can be used to compute the square root in number systems other than the decimal number system. For instance, finding the digit-by-digit square root in the binary number system is quite efficient since the value of is searched from a smaller set of binary digits 0, 1. This makes the computation faster, since at each stage the value of is either for or for. The fact that we have only two possible options for also makes the process of deciding the value of at theatrical stage of calculation easier. This is because we only need to check it for if this condition is satisfied, then we take, if not then also. The fact that multiplication by 2 is done by left bit shifts helps in the computation. Decimal: write the original number in decimal form. The numbers are written similar to the long division algorithm, and, as in long division, the root will be written on the line above. Now separate the digits into pairs, starting from the decimal point and going both left and right. The decimal point of the root will be above the decimal point of the square. One digit of the root will appear above each pair of digits of the square. Beginning with the leftmost pair of digits, do the following procedure for each pair. Starting on the left, bring down the most significant pair of digits not yet used and write them to the right of the remainder from the previous step. In other words, multiply the remainder by 100 and add the two digits. This will be the current value c. Find p, y and x, as follows. Let p be the part of the root found so far, ignoring any decimal point. Determine the greatest digit x such that we will use a new variable y equals x. Note: 20p plus x is simply twice p, with the digit x appended to the right. Note: you can find x by guessing what c is and doing a trial calculation of y, then adjusting x upward or downward as necessary. Place the digit as the next digit of the root, i.e., above the two digits of the square you just brought down. Thus the next p will be the old p times 10 plus x. Subtract y from c to form a new remainder. If the remainder is 0 and there are no more digits to bring down, then the algorithm has terminated. Otherwise, go back to step 1 for another iteration. Examples: find the square root of 152.2756. 1, 2, 3, 4, 152.2756, 1 asterisk 1 less than equals 1 less than 2 asterisk 2 x equals 101 y equals x asterisk x equals 1 asterisk 1 equals 1005222 asterisk 2 less than equals 52 less than 23 asterisk 3 x equals 20044 y equals asterisk x equals 22 asterisk 2 equals 440827 asterisk 3 less than equals 827 less than 244 asterisk 4x equals 30729 y equals asterisk x equals 243 asterisk 3 equals 72998562464 asterisk 4 less than equals 9856 less than 2465 asterisk 5 x equals 49856 y equals asterisk x equals 2464 asterisk 4 equals 98560000 algorithm terminates. Answer is 12.34. Find the square root of 2. 14142 200 2 1 asterisk 1 less than equals 2 less than 2 asterisk 2 x equals 101 y equals x asterisk x equals 1 asterisk 1 equals 1 1 24 asterisk 4 less than equals 100 less than 25 asterisk 5 x equals 4 96 y equals asterisk x equals 24 asterisk 4 equals 9604 281 asterisk 1 less than equals 400 less than 282 asterisk 2 x equals 10281 y equals asterisk x equals 281 asterisk 1 equals 281 2824 asterisk 4 less than equals 11900 less than 2825 asterisk 5 x equals 4011296 y equals asterisk x equals 2824 asterisk 4 equals 112960604 28282 asterisk 2 less than equals 60400 less than 28,283 asterisk 3x equals 2. The desired precision is achieved. The square root of 2 is about 1.4142. Binary numeral system inherent to digit-by-digit algorithms is a search and test step. Find a digit, when added to the right of a current solution, such that, where is the value for which a root is desired, expanding the current value of, or, usually, the remainder, can be incrementally updated efficiently when working in binary, as the value of will have a single bit set, and the operations needed to compute and can be replaced with faster bit shift operations. Example: here we obtain the square root of 81, which when converted into binary gives 1,010,001. The numbers in the left column gives the option between that number or 0 to be used for subtraction at that stage of computation. The final answer is 1001, which in decimal is 9.1001, square root 101.0001, 111 101 01 1001 100 1001 1001 1001. This gives rise to simple computer implementations. Short ISQRT, short res equals 0, short bit equals 1 less than 14. The second to top bit is set 1 less than 30 for 32 bits. Bit starts at the highest power of 4 less than equals the argument, while bit greater than equals 2, while, if num equals res plus bit, res equals plus bit, else res greater than equals 1, bit greater than equals 2, return res, using the notation above. The variable bit corresponds to which is the variable res is equal to, and the variable num is equal to the current, which is the difference of the number we want the square root of and the square of our current approximation with all bits set up to. Thus, in the first loop, we want to find the highest power of 4 in bit to find the highest power of 2 in. In the second loop, if num is greater than res plus bit, then is greater than, and we can subtract it. The next line, we want to add to, which means we want to add to, so we want res equals res plus bit less than 1. Then update to inside res, which involves dividing by 2 or another shift to the right. Combining these two into one line leads to res equals res greater than 1 plus bit. If isn't greater than, then we just update to inside res and divide it by 2. Then we update to in bit by dividing it by 4. The final iteration of the second loop has bit equal to 1 and will cause update of to run y extra time, removing the factor of 2 from res, making it r. Integer approximation of the root. Faster algorithms, in binary and decimal or any other base, can be realized by using lookup tables, in effect trading more storage space for reduced runtime. Exponential identity. Pocket calculators typically implement good routines to compute the exponential function and the natural logarithm, and then compute the square root of s using the identity found using the properties of logarithms. The denominator in the fraction corresponds to the nth root. In the case above, the denominator is 2, hence the equation specifies that the square root is to be found. The same identity is used when computing square roots with logarithm tables or slide rules. Back-Charlie approximation. It is equivalent to 2 iterations of the Babylonian method beginning with n. The original presentation goes as follows. To calculate, let n2 be the nearest perfect square to s. Then, calculate. This can be also written as example. Find Vedic duplex method for extracting a square root. The Vedic duplex method from the book Vedic Mathematics is a variant of the digit-by-digit method for calculating the square root. The duplex is the square of the central digit plus double the cross product of digits equidistant from the center. The duplex is computed from the quotient digits computed thus far, but after the initial digits. The duplex is subtracted from the dividend digit prior to the second subtraction for the product of the quotient digit times the divisor digit. For perfect squares, the duplex and the dividend will get smaller and reach 0 after a few steps. For non-perfect squares, the decimal value of the square root can be calculated to any precision desired. However, as the decimal places proliferate, the duplex adjustment gets larger and longer to calculate. The duplex method follows the Vedic ideal for an algorithm, one-line, mental calculation. It is flexible in choosing the first digit group and the divisor. Small divisors are to be avoided by starting with a larger initial group. Basic principle: we proceed as with the digit-by-digit calculation by assuming that we want to express a number n as a square of the sum of n positive numbers as defined divisor as and the duplex for a sequence of m numbers as thus. We can re-express the above identity in terms of the divisor and the duplexes as now the computation can proceed by recursively guessing the values of so that such that for all. With initialization, when the algorithm terminates and the sum of s give the square root. The method is more similar to long division, whereas the dividend n is the remainder. For the case of decimal numbers, if where, then the initiation and the divisor will be. Also the product at any m theatrical stage will be and the duplexes will be, where are the duplexes of the sequence. As in any m theatrical stage, we see that the place value of the duplex is 1 less than the product. Thus, in actual calculations it is customary to subtract the duplex value of the m theatrical stage at theatrical stage. Also, unlike the previous digit-by-digit square root calculation, where at any given m theatrical stage, the calculation is done by taking the most significant pair of digits of the remaining term. The duplex method uses only a single most significant digitive. In other words, to calculate the duplex of a number, double the product of each pair of equidistant digits plus the square of the center digit. Number equals greater than calculation equals duplex 3 equals greater than 32 equals 914 equals greater than 2 equals 8574 equals greater than 2 plus 72 equals 89 1421 equals greater than 2 plus 2 equals 2 plus 16 equals 18 10523 equals greater than 2 plus 2 plus 50 32 equals 6 plus 0 plus 25 equals 31. 406,739 equals greater than 2 plus 2 equals 72 plus 0 plus 84 equals 156. In a square root calculation, the quotient digit set increases incrementally for each step. Example, consider the perfect square 2809 equals 532. Use the duplex method to find the square root of 2809. Set down the number in groups of 2 digits. Define a divisor, a dividend and a quotient to find the root. Given 2809. Consider the first group 28. Find the nearest perfect square below that group. The root of that perfect square is the first digit of our root. Since 28 greater than 25 and 25 equals 52, take 5 as the first digit in the square root. For the divisor, take double this first digit, which is 10. Next, set up a division framework with a colon. 2809 is the dividend and 5 is the quotient. Put a colon to the right of 28 and 5 and keep the colons lined up vertically. The duplex is calculated only on quotient digits to the right of the colon. Calculate the remainder. 28 minus 25 is 3. Append the remainder on the left of the next digit to get the new dividend. Here, append 3 to the next dividend digit 0, which makes the new dividend 30. The divisor 10 goes into 30 just 3 times. Repeat the operation. The 0 remainder appended to 9. 9 is the next dividend. This provides a digit to the right of the colon, so deduct the duplex. 32 equals 9. Subtracting this duplex from the dividend 9, a 0 remainder results. 10 into 0 is 0. The next root digit is 0. The next duplex is 2 equals 0. The dividend is 0. This is an exact square root. 53. Find the square root of 2809. Set down the number in groups of 2 digits. The number of groups gives the number of whole digits in the root. Put a colon after the first group, 28, to separate it from the first group, 28. Obtain the divisor, 10, since 28 greater than 25 equals 52, and by doubling this first root, 2 by 5 equals 10. Gross dividend, 2809. Using mental math. Divisor, 10, 30 square, 10, 28. 39 duplex. Deduction, 25. XX09 square root. 5 to 3. 0 dividend. 30 remainder. 300 square root. Quotient. 5 to 3. 082 variable iterative method. This method is applicable for finding the square root of and converges best for. This, however, is no real limitation for a computer-based calculation, as in base-2 floating point and fixed point representations. It is trivial to multiply by an integer power of 4, and therefore by the corresponding power of 2, by changing the exponent or by shifting, respectively. Therefore, can be moved to the range. Moreover, the following method does not employ general divisions, but only additions, subtractions, multiplications, and divisions by powers of 2, which are again trivial to implement. A disadvantage of the method is that numerical errors accumulate, in contrast to single-variable iterative methods such as the Babylonian one. The initialization step of this method is while the iterative steps read then. Note that the convergence of, and therefore also of, is quadratic. The proof of the method is rather easy. First, rewrite the iterative definition of as. Then it is straightforward to prove by induction that and therefore the convergence of to the desired result is ensured by the convergence of to 0, which in turn follows from. This method was developed around 1950 by M. V. Wilkes, J. Wheeler and S. Gill for use on EDSAC, one of the first electronic computers. The method was later generalized, allowing the computation of non-square roots.